here's a quick agenda of what I'll be talking about today. So first I'll give like a high-level overview of deep learning and focusing more on the inference side. And then I'll dive a little deeper into the Nvidia TensorRT inference server, which is the product that I focus on, and the features that go into it, the overall architecture, the ecosystem. I'll do a quick performance slide and then the demo. And then I'll hand it over to Pete to talk about the inference server on OpenShift. But before I get started, I did want to do a quick show of hands. How many of you all are involved in deep learning workloads right now? Okay. How many people plan to work on deep learning soon? Okay. So if you're not aware, deep learning is the technique of using massive amounts of data to train neural networks to be able to make human-like decisions. So you start off with an untrained model, and you do several iterations of a large data set on this neural network, and outcome is a trained neural network that can now make human-like decisions. So in this case, it's a simple image classification use case where images are passed in, and the network can now figure out if it's a cat or a dog or whatever. And now inference, which is what I'll be focusing on most of this talk, is the idea of taking that trained neural network and then putting that and deploying that into the real world to make decisions on data that it hasn't seen before. So training, it uses the same kind of set to train on, and then in inference, it's new data. And then there's this idea of plaster, which stands for programmability, low latency, accuracy, size of network, throughput, efficiency, and rate of learning. So this kind of goes into why GPUs are necessary for this inference process of deep learning. And as you can see, latency is not the only factor that goes into a successful inference deployment. There's things like accuracy as well. So if you think about use cases like autonomous vehicles, you not only need your decisions to be made fast, but also highly accurate. And using GPUs for inference delivers on all these factors. So here are some of the pain points that we typically see with end users of these deep learning inference deployments. So the main problem here is the problem of inefficiency. So the first one here is only being able to run a single model on a single GPU at a time. And so if you have a use case like here on the far left, if you have an ASR model, a natural language processing model, and a recommendation model all running in your data center, and they each have a dedicated GPU, and let's say the ASR model traffic spikes, the rest of the GPUs are left underutilized, which is highly inefficient. Another pain point is having only a single framework support, and this restricts teams to only use one framework. So if there are several teams and they want to develop in PyTorch, TensorFlow, and Caffe, they would all have to build out their own custom pipeline, which is not efficient as well. And then similarly with custom development, if you have several teams each doing their own pipeline, one for each use case that they're deploying, if every single team builds out their own custom pipeline, that's not efficient because they're all really doing the same underlying task, which is inference. And so having one solution that manages all these pipelines makes that portion easier. So this is just a quick high-level overview of the TensorRT inference server and where it sits in the ecosystem. So here on the left, you see the clients sending their requests into some cloud application, or several applications, it might be. And then those requests are sent to a load balancer, where those requests are then, the traffic is sent to the appropriate instance of the inference server. So you may have several instances of this inference server, and all underlying hardware is visible, including heterogeneous GPUs, which is why we have Tesla T4, V100, and P4 listed here. And this is helpful if you have new hardware being integrated into a data center. You wouldn't have to reconfigure your software for that. It integrates with orchestration systems such as Kubernetes, and it's now open source for further customization. So the inference server has several features, and just to point out a few here in green, I mentioned being able to run multiple models concurrently on a single GPU. You can run multiple models and multiple versions of the same model at the same time on a single GPU. And this is what really lets you utilize your GPU to its maximum capacity. And then another useful feature is dynamic batching. And so when client requests come in, they come in without any logic. They come in at batch size 1. And being able to, the inference server can take those batch size 1 and batch them internally to be sent to execution in the backend at the same time. So the user wouldn't have to build that logic outside of the inference server. And those are based on a user-defined SLA, latency SLA. The inference server also exposes Prometheus metrics, and those metrics include utilization, memory, count, and latency. And these metrics help with making auto-scaling decisions, knowing when to scale up and scale down your instances of the inference server. And then I also mentioned multiple model format support, and the models, the formats supported are TensorFlow, GraphDef, and saved model. We also have this TensorFlow, TensorRT integration that's also supported. Of course, TensorRT plans, and then Caffe to NetDef through the Onyx path. And then the newest feature is, that we'll be announcing soon, is the streaming API. And this allows for support for sequence models that have input, that have state associated with it. So use cases like speech recognition and translation are also supported now. So this dives a little bit deeper into the inference server architecture, the internal architecture. So this green box here represents the inference server. And at the top, you see the client requests coming in through HTTP or gRPC. And so there's also this Python and C++ client library that helps with this interaction between client and server. And so once client requests come in, they go through request and response handling. And here you can see it's a simple image classification use case similar to the example I showed before for classifying these images. And so then what happens is that request goes through the per model scheduling queues. So for example, if this request needed a ResNet 50 model, it would go to the ResNet 50 queue. If it needed an inception model, it would go to that one, and so forth. And then through there, it goes to the framework backend. So if that model was in TensorFlow, it would go to the TensorFlow backend. If it was a TensorRT model, it would go to that backend, and so forth. And then from there, the request gets sent back through handling and back to the client. A few things you'll notice is the metrics are exposed through a separate HTTP endpoint. And then at the top, you'll see the model repository. And this is where models are placed after training is done, and they're already in the format that is for the inference server, so like the ones that I mentioned, GraphDef, Save Model, and NetDef, and plans. So those will be placed into a persistent volume here called the model repository. And like I mentioned before, all hardware is visible to the inference server, including CPU. So like I mentioned, there's a new streaming API. And just to explain kind of briefly what this example is showing. So if you have speech recognition sort of use cases, the packets come in one at a time, and they have these correlation IDs that go along with them. And once they come into the inference server, they go similarly to the per model scheduling queues. And what's new here is that before I showed that the batcher, which was the per model scheduling queues and the dynamic batcher. Now what's new is the sequence batcher that takes those correlation IDs and uses them to direct the packets to the particular inference server instance that executed the previous packet. So it's a bit complicated there, but what's important here is that packets of the same sequence need to go to the same batch slot here for execution. And so this sequence batcher is what has been built out recently in the inference server. So up until now, we've been taking kind of a zoomed in view of what the inference server has internally, and now we're taking a step back and seeing how it fits into the larger ecosystem here. And so here on the right, you'll see the green boxes. Those are that's the TensorRT inference server, and you can have several instances of it running in your data center. And then on the left, you'll see this user client request coming in, and then this box with these three components, the client API, pre and post processing. So this is what we like to call the app, whatever it may be. So for, like I've been using this image classification use case, this would be where an image comes in and maybe it needs to be resized or cropped to be able to be fed into the neural network that's needed for the result. So that's where that would happen. And then the request would then go to a load balancer that directs traffic. And then at the top also I mentioned that if you have, you may do all your training of all your models and you put them in some network file storage. That would, a subset of those models that want to be deployed would have to be separated out into this persistent volume, which is called the model repository. And that's mounted into the TensorRT inference server. From there, the TensorRT is taking these requests and then performing the inference and sending the result back. And while it's doing all that, it's also exposing these Prometheus metrics through HTTP. And those can also be connected to an autoscaler for further scaling up and down. You'll also notice this, this dotted line box, and that's where we've had our collaboration with Kubeflow. TensorRT's inference server is now supported in Kubeflow, and the goal is to kind of extend this box and include the load balancer as well. So that's also supported. And so here's a quick performance slide. Key takeaways here are that this is a ResNet 50, several deployments of ResNet 50 on TensorFlow FP32 on CPU, which is this blue line, and then TensorFlow, the same model on GPU, and then the TensorRT plan, which is a highly optimized version of the same model through the TensorRT framework. And you'll notice that there's a significant increase in the throughput here. And this is all under a 50 millisecond SLA. But the more important thing to take away from here is that the inference server supports CPU, GPU, and multiple model frameworks like TensorFlow and TensorRT. So here's a video of, if you were at KubeCon last year or in December, you might have seen the live version of this demo being shown at our booth. But here's just a quick video. And I'll probably just explain what's going on since it's a little busy, but at the top is our this is our Flowers demo to show off the inference server. And at the top you'll see is the Flowers client, which is doing several classifications of these flower images. And that flashing light indicates how many images are being performing inference on right now. So you'll notice at the bottom left, you'll see demand and delivered. So there's 800 images per second of demand, and it's being met. And so on the bottom left, you'll see that this is 8 GPUs at the bottom, so 2 blue, and the different colors at the bottom indicate different models. So the blue indicates this Flowers model. And right now you'll notice that the utilization across all the dials, that shows per GPU utilization, and then the bigger dial is the overall GPU utilization, so fairly low as of right now. And then, so that's kind of what you're looking at. And I'll skip forward a little bit just to show some changes. So what you'll see soon is that we'll increase the demand. We'll increase the demand to the same cluster so we've increased the demand to 5,000 images per second now, and all the traffic is being sent to this cluster that has one GPU supporting each model. So you'll notice this spike over here on the chart where the Flowers model has spiked in requests now to 5,000, and these 2 GPUs supporting that model have maxed out in GPU utilization. And you'll notice that the other GPUs supporting other models are not being utilized at all. So obviously this is not efficient, and we're not even meeting the demand of 5,000 images per second here. And so if I were to skip forward a bit, a typical solution here would be to increase more hardware to support that model, but you still are left with GPUs underutilized. So now what has been done is the traffic is now sent to a different cluster. At the bottom right of the screen, you'll see that this is a different, these are all Kubernetes clusters, by the way. And each GPU has every single model loaded onto it, hence the multicolored colors inside the boxes of each GPU. And so now you'll see that it's easily meeting the 5,000 images per second demand on this cluster that has the TensorRT inference server running on it. So all the GPU's utilization is about 30–40%, and the overall GPU utilization is around the same. And we're easily meeting that demand. And so with this configuration using the TensorRT inference server, there's a lot of capacity to add more traffic. And so what we can actually do here is increase the traffic or increase the demand, or now what we're doing is actually simulating a kind of jumpy traffic pattern and going up and down, and we've actually scaled it all the way up to 15,000 images per second. And the inference server enabled cluster is maxing out on all 8 GPUs utilization and getting the maximum utilization of all of those GPUs. And looks like we actually went all the way up to 17,500 or 18,000 images per second, and it's able to manage that load as well. So that's pretty much it for the demo. And so I have some resources here, including our data center inference page, where you can learn more about our deep learning inference products, such as TensorRT and the inference server as well. And the TensorRT inference server is available on our NGC NVIDIA GPU Cloud Registry as a container. And it's also open source, like I mentioned, and the GitHub repo is right there as well. And for getting started, we have this engineering developer blog that walks you through a really useful, simple example that you can just get started with. And there's another guest blog that we did with Kubeflow explaining our integration with them as well. So that's it from me. I'll pass it over to Pete now.
So obviously, the star of the show is TensorRT Inference Server. This is a nice sort of quick little demo that hopefully illustrates how this can be deployed on OpenShift. So the structure of the demo is we have 2 pods. There's one for the inference server, another for a inference client, and then a OpenShift service defined for the server. That's the communication path for the client to the server. And then there will be a PVC and PV making use of local storage, where we store some pre-built models for ResNet and Inception. So sort of architecturally, this is what the demo looks like. Again, the communication path there is in what we would call sort of the pod layer, is from the client to the service endpoint for the inference server. And the inference server pod is basically attached to this storage layer where it has the models. Sorry, Tripti, I don't know if that's used at
just
NVIDIA.
Say inference server.
Inference server.
Yeah.
Sorry, TensorRT Inference Server. It's sort of a shorthand for this demo. That's my bad, I think.
That's fine.
So yeah, that's the idea there. So the server image, in terms of image, we're talking about the image that was created by Nvidia. The client image that's used in this demo is built from the publicly available Docker file that's on the Nvidia GitHub repo. And then they have a set of models that we can load into the inference server, just a simple one, ResNet 50 and Inception v3. And we run the demo on an Nvidia V100 16 gigabyte card there. So this is all using OpenShift 3.11. All right. So let's look at our project. Again, this shorthand, this unofficial nomenclature, TRTIS. So we have basically our application here and a pair of pods. So let's have a look at the inference server pod. And the logs for that indicate a successful start of the inference server in that pod. It's actually exposing a couple endpoints. There's one for HTTP REST and the other one for gRPC, as Tripti mentioned. Those 2 capabilities are in place, and we expose them through OpenShift. And then from the logging, we can tell, basically it'll sit there, I believe, and pull for models in the storage location. So we've dropped some models in there, and it picked them up, and it's basically gone through its setup for setting up inference serving of those models. Okay, so that's the server itself. Oh, and that's services. Let's go back to pods. Let's go to the client, and let's do a terminal here. And let's see if it remembers any of the commands. So let's run. So the image client here is a pre-built C++ client within this client pod. So we're going to work against the REST service to begin with, and we're going to run inference on a couple of images. In this case, it's a mug, and let's see how it does. Coffee mug.
Any way to make that font?
Oh, Diane, of course there is. It's not just me, right? Yeah, let's run that again. How's that? Better? And what other? Okay, let's see if we can throw some other commands at it. There's a nice suite of tools there that live demo, Diane. This is what you got. This is what you got. There we go. So we have some sort of commands teed up there. That first one was the basic HTTP test. You can run it again against gRPC. We'll find its, let's go back over here and up here and paste that in there, and it's quite a bit faster. Oh, I'm going to have to scale that back. Sorry, Diane. And then finally, there's a benchmark test. So there's various different modes with the clients. You can do batch inference and things like that. We'll finish off here in the demo with a performance benchmark. Again, that's provided by Nvidia for us. And let's make that full screen so we can see the full. Oh. Yeah, so it ran the benchmark there. That's pretty much it. So you can see it through the console. Basically, this interaction between the inference server, the models that have been stored for it. That storage could, of course, be Ceph. For the purpose of the demo, is just put into local storage. And then the interaction between components in OpenShift and Kubernetes, we've put together a client for that. So that's pretty much it for the demo.
Thanks.
Yeah, okay, thank you.